Hasan from VB8, and he's talking about a very interesting topic I think not many of us are already doing. It's about multimodal retrieval and generation, using embeddings again, and using VB8 for that. And I think there's also some live coding part of it, so I'm really looking forward to it. So, Zain, the stage is yours.
Awesome. Thank you. So, hey, everybody. My talk is about multimodal models. So it's embedding-based retrieval, but now the embeddings are multimodal. They understand different types of data. And I'm going to be talking about how you can scale this up with vector databases so that you can apply it to things like recommendation systems. Before I get going, I wanted to start off with a question here. Okay. So how many people here think that AI poses an existential threat to humans in the next 5 years? If yes, just hands up. If no, hands down. 1, 2, nobody. 3, only 3 people. Okay. So this is not a gotcha question. This is actually a question that was posed a few months ago in Toronto for a debate. And these are some widely known scholars in the field of AI. And there's giants on either side of this debate. And this took place in Toronto. I'm from Toronto. And they both had good cases to make. And so I expect to see more people put their hand up for that. But of the people that did put their hand up, I had follow-up questions. So if you do say that within 5 years we'll have AI that can that'll be an existential threat, then the question is, why don't we have AI that can do any of these things that I'll list out? Right? We don't have AI that can drive reliably, right? But driving is a pretty high bar, right? Humans probably can't even do that. So let me make it even easier, right? We don't have AI that can cook a meal properly. So I'm not just talking about kind of spilling a few ingredients into the bowl. I'm talking about the whole cooking a meal from the beginning, you know. And then we can just keep on decreasing the bar. We don't even have robots that can set up a table, walk naturally. Human gait is actually a very nuanced phenomenon. We don't have robots that can properly achieve something as simple as human gait, right? And then you can keep on decreasing the bar, and we don't have AI that can appropriately accomplish these very simple, trivial things. And so this is actually known as Moravec's paradox, where for AI, there are things, compute-related things that are very easy, trivially easy. Language translation, playing chess, calculating integrals are super easy for AI, and we have AI that can do it 1,000 times faster and more accurately than humans. Whereas on the other side, you have things which are insanely hard for AI to do. Right? We don't have AI that can run, can walk, can see, recognize, that can smell. And the paradox here is that for humans, it's exactly the opposite. So the paradox says that reasoning requires very little compute, whereas these additional sensory phenomenon, walking, running, seeing, feeling, touching, requires an insane amount of compute that humans cannot currently accomplish. And so the idea here is that the way that we're training, or the way that biological intelligence is trained, and the way that machine intelligence is trained is quite different. Right? So there is something missing. And before we can get to an existential threat, we need AI that can do things on the right hand of the side here. And so we're missing something, and there's scientists who believe that what we're missing is thinking about how humans learn. So if we think about how humans learn, I have a son who's 11 months old. He's going to be a full year in October, and just observing what he does and how he does it, he doesn't speak a word, right? But he touches objects, he plays with things, he'll put things in his mouth, he'll taste them, smell them, he'll do all sorts of interesting things, and he's learning through all these interactions, right? When he used to fall, he used to get hurt, but now that he falls, he's learned how to balance and fall just the right way. So he's learning how to do all these things without speaking. And that's what humans do. We build a foundation you could say a world model within the first year that's multimodal, right? It's through touch, feel, smell, and a lot of it is non-lingual. And then on top of this foundation that we've built, we use language to learn more and more advanced skills. And language is a bit of a catalyst to learn more abstract concepts as opposed to learning base concepts. So what it seems like we're missing right now is this multimodality. We have a lot of language, so we've got large language models, but we don't have large multimodal models. Right? And so the whole talk revolves around this concept of multimodal models that promise us these human-like capabilities, the ability to understand touch, the ability to understand a data point from all of its other perspectives outside of just the unimodal component that it's been trained on. So if we think about a data point, the reason why humans are so good at learning things in a very few shot manner is because we can take a data point and deconstruct it into its multiple modalities. So if I take my son to the park and I tell him that that's a dog, he'll look at the dog, he'll see how the fur waves on the dog, he can touch the dog, he can hear the dog. A data point can be deconstructed into all these modalities and then understood. Right? So it's not just the way the dog looks, but the way the dog barks, the way the dog moves. All of these kind of come together to define the concept of a dog, which makes it a lot more efficient to learn these concepts. We want to have models that understand data point from this perspective as well. So here are some modalities, some of which our ML models are already good at. So that being language, image, audio. And then on the right, we have some modalities that our models are not so good at, especially the combinations of sensory motor, proprioception, and then doing tasks over this type of input. So the promise of ML multimodal models is we want to have one model that understands across these modalities. And because it understands across these modalities, you can then perform downstream tasks that seem a lot more complicated than what we have capabilities to do right now. So this is what we'd like to accomplish. And I wanted to go into how this is possible or how this is currently done. And then we can talk about whether it's scalable or not. And this is interesting work. Our ability to digitize different modalities is changing every day. I'll just let it pass. Recently, there was a new paper that was published that can even digitize smell. Right? So you could take molecules and you can build up a embedding model, an odor map, where each one of these molecules is one vector here. So you could tell when something stinks or smells good. So now you have this ability to vectorize smell, and then now you can perform search over this as well. So slowly but surely, we're adding all these modalities to our repertoire. Now, this is not widely accessible. This is work out of Google that was spun off and is now a startup. But in the next 5 years, we'll be able to digitize smell as well. So then the question is, how do multimodal models work? Right? How do they understand all of these different modalities and then allow us to do cross-modal reasoning? So there's multiple answers, but the one that works well currently is that you train one model per data type. So I'll play an image here from a paper that was released recently. Oh. So you train one model per data type. So I'll have a text model, an audio model, a model that understands images and video, a model that understands motion, IMU. So these are accelerometers. And then what you do is you unify them all. So it's kind of like taking a concept, translating into multiple languages, and then having a way to convert it into a universal language that the model can then use to understand concepts across language. So this trick is unifying, which is a bit difficult. I wanted to spend some time on the unification of these models. So on the data point level, let's say you start off with 3 embeddings. You have a reference embedding, the anchor there, and then you've got a data point that's dissimilar to the anchor, so it's a negative sample, and you have a data point that's similar to the anchor. And what we'd like in embedding space is for the similar data points to be closer together and the dissimilar data points to be farther apart. So we define some sort of loss function that then allows us to optimize this, right? The positive points get pulled together in embedding space, and the dissimilar points get pushed apart in embedding space. To kind of concretize this idea, let me show you a unimodal example. Let's say we're only working with images. We can have an anchor image, and then we could say augment or modify that image, turn it into a black and white image, and say that that's a positive example. So if we get the embedding for the middle image and the top image, we'd like those two embeddings to be closer together. And for the negative example, we'd like the embedding for that to be farther apart. So we're passing it through the same encoder, and then we're making sure that we minimize the difference between the vectors of the top two images, and we maximize the difference between the images on the bottom two images here. And so you don't really have two separate functions. You can actually squish it into one loss function and then optimize over it. And in action, this is what it kind of looks like. So you start off with multiple modalities all embedded into the same dimension. And then as you train over this contrastive loss function, similar data points get pulled together in embedding space and dissimilar data points get pushed apart. And they themselves get pulled together with similar data points of their own category. And then you can expand this to multimodal contrastive learning as well. So imagine you have two different embedding spaces, and the dimensionality of the embedding spaces is exactly the same. So you have concepts written down in text, and then you have the exact same concepts in video form. What you can do is define this cross-modal contrastive learning, where you join them into the same embedding space, and then you use this idea of positive and negative examples to pull and push data points that should be similar. Right? So you do this across modalities. So you can have, for example, the video of a lion and the description of a lion, and you want those two data points to be pulled together. Right? So that's an example of positive intermodality relationship. And then you can also do pushing and pulling within the modality level. Right? So you can have text that is not related to each other that you want to push away, and you can have text that is related that you want to pull together. So all of this to say that we need some sort of joint embedding space where we have concepts that are similar, that are in closer proximity versus concepts that are different, that are further away. If you want to learn a little bit more about this, there's a really nice paper here that that you can look at, and I'll share these slides afterwards for all these references as well. Okay, so this detour to get this one unified vector space. Right? So we've got all of these modalities at the bottom: language, image, audio, sensory motor, proprioception, speech. These go into one model. You could train individual models, and then it unifies them so that you can have vectors that exist in the same embedding space. So you could have images with text, with audio, with video. And the cool thing about having one unified vector space is that now you can do vector search over this using a vector database. Right? So I could have a data point represented as any of these modalities, and I could say what other objects are close to it in my vector space. So if you have this, it takes a lot to get to this point, but if you do have this, this unlocks a lot of cross-modal functionality, which turns out to be very useful. And in the second part of my talk, I'll talk about how this might be relevant for search relevance and for recommender systems. But for now, I'll just list them out. You can do cross-modal retrieval. So if you know of a concept in one modality, you can retrieve it in any other modality. You can have the sound of a train horn, and you can extract the image or the video of that concept. This is also known as any-to-any retrieval, where given any type of modality, you can retrieve any other type of modality as well. You can do embedding space arithmetic, which seems like a toy example, but there's a really nice application of this. You could add an image to audio, but the application of this is that you can do multimodal querying. So if you have a concept that you know how it looks and how it sounds, you can now combine those two vectors into one query, and then you could say, I want another similar product that looks the same and sounds the same as well. So you could do multimodal querying, which I'll also talk about. So people have explored these concepts in separate detail. And then, of course, a lot of people are interested in this generation using these generative models. You can now do any-to-any generation as well. If you have models that can generate images, then you can prime them with modalities that they also understand. And this is all from one paper, ImageBind, that works great in practice. So what we did is we integrated this into Weaviate, the vector database, so that you can use it to embed your own data, and then you can search over it, and you have all of these functionalities enabled. And so the goal here being that you can reason over these modalities if you have the ability to represent all of them in a unified vector space. Okay, so I want to break here and show you an example of this working in Weaviate. I could zoom out. Yeah. All right. So this is a demo app that we built, and I'll show it to you, and then I'll try to see if you can understand how this might be working. Let me zoom a bit here. Okay. So this is my text query. This goes in, and I could search things, and we'll have images that come up. We'll have video that comes up as well. Another image. We'll have, one second, let me turn on the audio. So we've extracted all these modalities because we've got a unified vector space. This is probably the least coolest of these searches. I want to do some more cool searches. But can anybody understand what's going on here? Yeah. So when I asked this question before going over priming people with multimodal models, they talk about metadata and how the audio might have some concept of a car, or maybe you're searching over the name, and that's how it understands that you're actually looking for a car. So the name of this file is car. No, what's actually happening here is that it's taking the audio, it's running it through a audio model, and it's generating a vector embedding for this. And it's recognizing that the vector embedding for this query, the city car, is in close proximity to the vector embedding for that audio sound, and then it's retrieving those and showing you those. But because this is a multimodal model, you can pass in any modality, and that can become the query as well. Okay, so let me demonstrate that as well. Let's say we pass in this as an input query. So we get back relevant results here, all images this time. I can do some more here. Do image search. Yeah, so this is pretty good. The reason why I chose to talk about this particular type of multimodal model is because it works well in practice. There's a separate type of multimodal model that trains one model on all this data. That's a lot more scalable, but it doesn't work as well currently. So the demos are not as interesting. And this is one of the reasons why we chose to integrate this as opposed to those other models. And then the last demo I'll do here is using audio to query. Right? So this is the query. So this is the query, and then these are the multimedia representations that come back, including the video here, and these are other images as well. This is locally running, so I could pass in a video, but I don't have GPU support, so it'll take a long time to embed that video, and then maybe I could. Well, actually, we'll leave it. I'll show at the end if people are interested. It takes a while to embed that video, but it does come up with relevant objects. Okay, so we've got this open source. If you want to try this with your own data set, feel free to do that. And if you have any questions, then we can take those up later as well. But now that we're all excited, hopefully we're going from this to this, right? And actually, there's been news that OpenAI and Google are doing the same. They're moving from large language models to now large multimodal models that can take in images and generate images as well. And then slowly but surely, we'll expand the multimodal capabilities there. But what I wanted to do in the second half of the talk is talk about applications, right? So a lot of you might be thinking, if you have the ability to generate vectors, then this is not very surprising, because a vector database can take those vectors and it doesn't care whether it's an image vector or a video vector. It'll just search over them. So what are some interesting applications of using multimodal models, and why this marriage of multimodal models with vector databases is actually really useful? So let me go into some examples here. The first example that I'll talk about, and this is actually 3 separate examples, is how you can improve e-commerce e-commerce and recommender systems with multimodal search, particularly search relevance as it pertains to this problem can be improved significantly. So the answer lies in this question. Whoops, I'm gonna move this slightly. So if I ask you what burger do you like, or what type of burger do you like, how could you answer this? So you could do it classically just by a text representation, right? So you could describe the type of burger that you like to me. But if you have a model that understands text, but also these other modalities, you could show me an image of the burger that you like. If you have a model that understands smell, you could say that I like this smell, this type of burger. Right? This might be a bit weird, but you can also tell me how it sounds when you eat it, or how the ingredients sound. Right? So now we're understanding a user's likes and dislikes across modalities, as opposed to just through one modality. Right? And so you can describe what a person likes through all of these modalities. And this is realistic because a company could take their product and invest money to explore it across multiple modalities. And then anytime somebody purchases that, you can kind of assign responsibility of why they purchased it across these modalities. And then it's not just the senses, but you can also have this contextual modality as well. I'll share a paper later on where Facebook, for their marketplace, they actually have a contextual modality that takes into account seller reliability, seller stars, the price of a product. So you could have something like nutritional facts, and that can also be a separate modality that can be fused into the representation of a burger that people like. And then you can embed this into vector space, but why just stick to one vector? We can barely represent text as one vector alone. So if you have all these modalities and all this information, ideally you want multiple vectors. These can be separate vectors. This could be a text vector, an image vector, a smell vector, or you can have different loadings or weightings of these vectors, and you can combine them depending on what type of search task you want. And so if we explore this idea further, why is it that having multimodality improves recommender system accuracy? The first thing is that it more uniquely allows you to identify what customers like, because now you have more senses or modalities to do so with. You can understand not just a description of something a customer likes or the way that it looks, but also how it sounds. And some modalities might be more important than other modalities for some products. You can also more uniquely compare relevance between products, right? So before you could compare text descriptions of two products, but now you can compare how they look as well. And I was having a conversation yesterday about products that might look the same, but the context might not be the same. The nutritionally, they might not be the same. You have more dimensions to do this comparison across now, which enables this last advantage, where even if you have products that look the same or have or are the same across some modalities, you have other modalities to differentiate them with. And this is work that was done by Amazon, and this is recent, just last month that was published, where they tried to do this multimodal modeling, and they said, if you have a query couch there and you want to see what other recommended couches show up, if you have a general model, this is something that might show up. So these are other things that you can sit on, and we can understand why this might be related. But if you train this in a multimodal manner, if you sharpen the unified embedding space, you can actually get really relevant results. So things that you can sit on, couches that look the same, feel the same, have the same material. And they showed that they can improve how relevant their search is based on this contrastive learning. So if we dig into this paper, there's two main concepts in this paper, actually. They do this general embedding where they take a product, its description, and they have two separate encoders. This is similar to CLIP, if you're familiar with that. They understand the description of a product and the image of the product, and they embed it into this unified vector space, but then they sharpen it. So they use these hard examples to then further push and pull on a smaller level within the category. So they'll take items in the same category, and then they'll push and pull differences within those items as well. And then they say we can take the image representation and the text representation and combine them just by adding the vectors and normalizing it, right? So they take the image vector here and the image vector and the text vector, they add it, and then they do a L2 norm to get this multimodal vector. And they showed that now if you do approximate nearest neighbor search here, you get a lot more relevant results that are returned because of this sharpening and because of the multimodality. Okay. So if we think further about what's enabled, this multimodality is definitely happening and it's helping. And the ability to do scalable search with vector databases over this amplifies this so that you can actually productize this multimodal search. But what's missing here? Right? We can do even better. There's more research that's been done recently that can further improve on this. So some of the problems, I think, with this approach is that they're equally weighting all the modalities. So the question is, why is image and text equally important in this space? Why should I just add the vectors and normalize them? What should happen is that depending on the recommender, the category that you're recommending, not all modalities are equal. Right? For some modalities, when I buy a shirt, I don't care about how it tastes. So the taste modality shouldn't matter for this recommendation task. For other recommendation tasks, particular other modalities might be overweighted. And the other thing that's happening is that they're using unimodal queries. So they're passing in images and performing this search. Why can't we do multimodal queries? So why don't we specify exactly what the user wants through a text description and an image description as well to more better localize exactly what they're looking for. So there's further work that was done on both of these questions. So there's a paper that was published this year about how we can prescribe meaning and prescribe importance or responsibility to how much each modality is contributing to an outcome. So this uses Shapley values. How many people here know what Shapley values are? Yeah, a lot of people. Okay, so Shapley values essentially allow you to assign responsibility to an input of a model and say how much that input is contributing to the output and nudging it in the positive or negative direction. So an example of this could be if I'm recommending burgers and I'm trying to break it down per modality, I can have a Shapley value per modality. So I can say, you know, the taste modality is particularly important here because it has a high Shapley value. The way that it looks and the way that I've described it is also important. But if I'm recommending a shirt, in this case, the Shapley value for taste, the taste modality is not that important because people don't care about it, whereas look and text are important in this case. So if you can train a downstream task and then you can extract Shapley values, then you can potentially use these Shapley values to weigh which modality should be more important or less important in a recommendation task. So you can take a model and see how reliant it is on one modality or the other. And you can also ask it for a given recommendation task, which modality matters more. And then you can weigh the inputs accordingly. So for some tasks, you might want to overweigh the way that a product looks versus the way that it's just described as text. And the second challenge here, building multimodal queries. So specifying what a user likes using image and text rather than just the image or just the text. There's multiple approaches to this. I don't think this is a solved problem, so there's new work that's coming out on this as well. But one way that this is done is in an end-to-end manner, where you have one model that understands both the image and the text of a query, and they rely on each other, so you can't use them by themselves. And you train this end-to-end, and then you extract from your knowledge base. And this is the simpler approach. The more complicated approach is by specifying this kind of synchronous, describing what you want here. So in this image, we can see a person, and then these are synced up with this kind of cursor across a canvas that shows I want the person in this region, I want the net and wall in this region, and it's kind of synced up based on the color code that's shown here. And the database takes this in and it extracts out exactly the thing that you want. Even if you might have other concepts that are similar, you can use this vision modality in the query to specify exactly what it is you want. Yeah. What's the time? How much time do I have? 10 minutes? Okay, cool. Perfect. Right. So that's one that's one example of why multimodality could help, and broken up into 3 different applications of it. Another thing that I want to talk about is what people are really interested in with respect to vector databases, this idea of retrieval augmented generation. But now that you have multimodal models, you can talk about multimodal RAG. And how this essentially works is if you have a generative model, whether it's multimodal or not, the issue is that it doesn't know what it doesn't know. Right? Anything that it's been trained on, it will give you a really smart answer. It can hallucinate as well, but it'll give you something. But something that it's not been trained on, it'll just tell you that this is outside my knowledge. So you can augment this with more information, right? So this is your typical vanilla ChatGPT prompt where you can pass in a question and then it answers it. Retrieval augmented generation is a very simple modification to this, where you say, here's something relevant. Before you answer my question, read over this stuff and then extract out relevant details from this, establish an understanding, and then give me a customized response. So this is what people are really interested in. It's known as RAG. But I wanted to talk about this at the end here, because now if you have the ability to retrieve both text, images, and multimodal concepts, and if you had multimodal models that can understand these modalities, now you can perform multimodal RAG. We're not seeing a lot of this in industry right now, but I think once we have large language models or large multimodal models that can understand these modalities, multimodal RAG will definitely be the next big thing. So how that works is you can have a retrieval system for this vector database that retrieves across modalities, so retrieves images, audio, just like I showed you in the demo here, and then it can build up this kind of candidate set of, these are the audio that you're interested in based on this prompt, the images and the text you're interested in, and then you can package them up and pass in all these different types of multimedia to deliver a customized response. And the utility of the vector database here is that you can scale it up as opposed to doing this slowly. And so multimodal RAG was recently described in a paper. I think this was 4 or 5 months ago, where people took a query and then they said, if we can retrieve from a multimodal database, so this could be a vector database that is linked to a multimodal model like the example that I showed you, where now given a query, it'll extract for you both a text and an image. Then you can augment your prompt with this text and image to better specify exactly what it is you want, and then you can generate more accurately. And so to enable this, you need both the first part of the ingredient, which I talked about, this multimodal models with some sort of retrieval system, a vector database, and you need a generative model that understands all of these modalities as well. And so in this paper, they actually showed if you just do unimodal retrieval augmented generation, you tend to get something similar to what you're interested in. If you do multimodal RAG, where you specify by text and image exactly what you want, you get a lot closer to, you can control the generation more finely. And this is a paper that recently came out that furthers this thinking, right? So this type of model can take in any type of modality that you're seeing here, including the important ones, text, image, audio, and video, and it can generate those as well. I've tried this. It doesn't work as well in practice, but this is the direction that we're heading. So probably in the next year, we'll have better and better multimodal models, and this will be more of a reality than it is now. And then outside of this, there's no reason why you should just stop at retrieving and generating. You can also use these things that we call generative feedback loops, where you can extract from a knowledge base and then send it to a language model as context, and then you can get it to generate and store that back into the database. And this makes it so that you can have continuous conversations with a language model or a generative model that has memory over previous conversations. So you can tell it to remember a concept, and it generates some sort of formulation, and then it stores it in its long-term memory, and then it can retrieve it later on as well. And so to enable this type of interaction, all you need to do is give it the ability to not just query a database, which RAG requires, but also the ability to delete memories. So delete objects from a database. So you can tell it to forget about the fact that I had a pet goldfish or something like that, and it'll delete that memory from the database. And even insert memory, so create new memory. So if you have another conversation and you tell it to remember this for next time, it'll insert it into the database, and then it'll be able to retrieve it next time, and it'll remember what you talked about. So the idea here, we're going from string matching, and hopefully we're really excited about multimodal search, specifically this idea of doing cross-modal search, understanding a product from different modalities, some of which might be more important than others for specific domains. And I really do believe this is the future. You can probably tell that I'm really passionate about this. If you're interested in this, connect with us. We think a lot about problems like this. So reach out to me. My colleague is here as well. If you have any questions, we'll take those. If you have questions later on, connect with me. I'm always happy to chat. Thank you, everybody.
Yeah, thank you, Zain, for the very inspiring talk. We have one question online from Max. He's asking, language models are trained on unlabeled texts. We can make these models large because they do not require human-generated labels. Yeah. How can we make large multimodal models without armies of labelers? In your opinion, how far can synthetic data get us?
Yeah, so we talked about contrastive learning. There's supervised contrastive learning, which Clip does. So you can take images and captions, and then you know that they're related because they're captions related to the image. But there's also unsupervised contrastive learning, which you can. So there's some modalities that actually you can take further than others. This is one of the limitations. Generating these positive-negative pairs by hand is a limitation, but I feel like you can still merge and fuse some modalities. So for example, audio, video, and text are three modalities that are probably the most important to us, and those are easy to merge because if you take a YouTube video, all three of those modalities are already merged into that one YouTube video, because you can take the image or the video representation, you can now transcribe it using Whisper any one of these models into text, and then you also have the audio. So for a lot of these modalities that we care about, we have tons and tons of data. Well, we don't, but Google does, or companies that might be able to create these models do. And then there's other modalities that are more difficult, right? So how do you generate lots and lots of data points for smell and taste? Those are unsolved problems. That's very difficult right now. But yeah, great question. That is one of the limitations.
Maybe any opinion on the synthetic data question? Can we generate enough synthetic data to help us, or?
I think in computer vision, they have proven that you can do this. So if you have a concept of a dog, you can turn it and say this is a synthetic representation of a dog. So that's another positive example. I don't know. I haven't seen that much of this in other modalities. I don't know if it's as possible. For computer vision, they have shown it, but I think that's already a solved problem. We have tons and tons of that data. We don't need more of that. So I haven't seen any good papers on different modalities, more unique modalities, synthetically augmenting these positive, negative examples.
Okay, thank you.
Thanks for talk. So I'm interested, as we are taking more and more modalities and projecting to the same vector space that captures all of this together, how big of the vector space we're going to need in the future to be able to decipher all of these different modalities and then distinguish between identical burgers, one that tastes soft and one that doesn't,
Yeah, I think there's two ways to think about it, right? You could increase the dimensionality of one vector space, or you could say that we can change how we combine across these representations. So you could have a representation of an overweight representation of smell and an overweight representation of taste, and then you can have a multi-vector representation across a lower dimensional vector space. I think that's more practical than just expanding, going from 1,000 dimensional to 2,000, 5,000, 10,000. And we're seeing people do this even with text now, right? So if you take a paragraph and you chunk it, you can have a vector representation for each chunk. and now a lot of these vector databases are moving towards a place where they support multiple vectors per document at different chunk levels. So maybe on the global level and then per sentence level as well. I think that's more practical, where you can take one product and have multiple vectors, and each vector can capture a separate modality. And then you can combine them differently, as I showed here. So if you have an image modality and a text modality, you can simply add them. That's the basic way to combine them. Or you could define interesting ways to combine them, like scrolling over an image to identify interesting concepts, and then extracting that image, those separate images into individual vectors, and then retrieving using that.
Okay, any other question in the audience? Not then, another round of applause for Zain.
Awesome.
And
Thank you.